Good morning, everybody. This is Julia Sanagata, one of Rumsey's automation managers, focusing on the automation and networking segment of our business and working with you, our customers, in those segments. So today our topic is Ethernet for automation, and I will turn it over to Dave Kang, who is one of our industrial networking and security specialists. Dave has been with us for several years now and has quite a background in the networking space, both on the enterprise side, kind of in the front office environment, as well as now many years here in the manufacturing environment.
Oh, thank you. Good morning, everyone. My name's Dave Kang. I'm one of the networking specialists with Rumsey Electric. In my past life, I spent more than 13 years in the IT world doing data centers, networking, business continuity, virtual migration, cloud migrations, etc. I made the transition in 2016 to OT networks and have since been specializing in industrial networking and doing analyses of the consequences of use of Ethernet on the plant floor and how to protect the performance of manufacturing networks. So here's what we'll be covering. Some background and some context first, defining Ethernet itself and Ethernet IP, how Ethernet IP traffic works, a review of multicast, and segmentation and visibility. The acceleration of the pace of Ethernet adoption, whether you're an OEM, end user, systems integrator, or whatever, has affected you in some probably negative way. Once upon a time, we had isolated networks that never really communicated with anything else. Industrial devices used to use only proprietary protocols without standards, often leveraging custom proprietary cable with custom pinouts. Most of my coworkers have desk drawers filled with specific cables that are only good for one particular device, only in the case we need to help support a legacy piece of equipment that's been in use for, 25 years plus. So what is Ethernet? When Ethernet was introduced to the industrial environment, it allowed a common standard-based application of media and equipment because everything was designed to speak the same language. We had improved connectivity and sharing of data, which resulted in the ability to make data-driven decisions, improve efficiency and efficacy, predict failure, and in the event of failure, respond more quickly to reduce downtime, and in the end, to make more money. With that interconnectivity, much like the growth of the Internet of Things in your own home, where you may have had a computer and your phone a few years ago, you probably have more computers, more phones, tablets, smart TVs, lighting systems, digital voice assistants, etc. And as everything has gotten a network connection in the home, so has everything on the plant floor. So what we're seeing now are networks that were never designed to accommodate the exponential growth in Ethernet devices that they are seeing. Everybody loves a cheap and cheerful solution, but in the long term, it's unsustainable and probably the primary reason a lot of you are here. So let's start at the beginning. Ethernet. That is the transmission of digital data via voltage value or a light on or off in the case of fiber optics, indicating a 1 or 0. This data from a source to a destination in the form of the general term packets over specific media type designated for Ethernet communications in accordance with IEEE standards. In most cases, a category or fiber optic cable. Here you see an example of a WIRESHARK packet capture identifying a source and a destination IP address. IP addresses are only one of the types of addresses involved with Ethernet. Every network interface card or NIC in the world has a unique address with the first 6 characters identifying the manufacturer and the rest to identify that device on any given network. This is written onto the hardware of the device and cannot be altered by normal means. You've probably seen them hundreds, if not thousands of times on a label side of the device. Address, on the other hand, is assigned by you, the user, and is not globally unique. The address allows identification of what network it is on and what number node they are on the network. So to reiterate, a MAC address is like your social security number. You receive this when you're born, you always have it, it is assigned to you, and it doesn't change. It identifies who you are. An IP address is like your current street address. You live there now, it indicates where you're located. The function of an Ethernet switch is to provide a reliable, efficient conduit for data to go from point A to point B. A switch does this by associating that MAC address of a connected device to a particular switch port on the switch. This in turn is stored in the MAC or CAM table depending on the manufacturer's name, so a switch knows how to reach any given device. A protocol called ARP, or Address Resolution Protocol, then associates the MAC address to the assigned IP address, thereby enabling endpoints to communicate with one another. So in the past, hubs were used which did not have this technology and simply flooded the entire network with data, assuming that the endpoint would be reached. This had a massive negative impact for networks such as collisions and rampant broadcast storms, as well as a tremendous amount of latency and jitter. Latency is the time a packet takes to reach its destination, while jitter is the change in that time. Reducing both creates a more deterministic or predictable network. Ways Ethernet communication is accomplished comes in three methods. So I'm going to start at the bottom here. Broadcast. A broadcast is a one-to-all single transmission, ensuring that all devices on the network receive the message. I mentioned ARP previously, as well as using the Ethernet IP driver in RS links. That's a broadcast message. This is how the Ethernet IP driver is able to browse and identify all the devices in a subnet in RS links. We have a multicast message. A multicast message is a one-to-many single transaction which sends information to a set of specific designated recipients. This is used for things such as SIP sync or SIP motion for high-speed time synchronization. The intent of multicast is to reduce network overhead by reducing the number of transmissions that are required. Now, theoretically, this is an excellent solution, but only if several things are true, which I'll touch on in a bit. We have unicast. It is a one-to-one transmission. In this example, the PLC on the left is sending data to all three of the PLCs on the right with individual messages for each. A message instruction in logics or the initial connection for a produce-consume connection is a good example of unicast traffic. You could see how this might produce additional stress on a network. Why would you go out to get one coffee 3 times when you could get all 3 at once? It doesn't make sense, right? This is far more time consuming and less efficient. So a good analogy is at an airport. A broadcast is an announcement that you shouldn't leave your baggage unattended, or the white zone is for immediate unloading and loading of passengers only, right? A multicast would pertain to all passengers of a particular flight. If you're not on that flight, you don't really care about it. Finally, a unicast is an announcement directed to you as an individual, telling you to report to the gate counter because it turns out they didn't oversell the flight after all, and you can fly standby.
So Dave, I think if we can pause on that slide for a second, it's really important on the plant floor as opposed to other environments that we all really understand this difference between broadcast and multicast and unicast traffic, because ultimately that has a great impact on the performance of the plant network, doesn't it?
Correct, yes. And this has to do with the network overhead generated from sending multiple messages. And we'll talk a little bit about how multicast and broadcast traffic can affect a network in the upcoming slides. So when a broadcast is transmitted, all the devices in that area can communicate with one another to receive the broadcast. In this example, you have switch 1, 2, and 3 in a typical flat network. Any device connected to these switches can be reached by the other and thereby constitutes a single larger broadcast domain. Broadcast traffic should be minimized due to the obvious effect of endpoints that don't need to hear a message shouldn't have to hear them, thus reducing the total amount of network traffic. So I just want to be clear with that. We're talking about the area in which a broadcast occurs. All the devices are going to receive this broadcast message, even if they don't need to hear it. That comes in really importantly when we talk about segmentation later. So some would then come to the conclusion that broadcast traffic is bad. That's not the case. Some broadcast traffic is absolutely required for Ethernet networks to function. I mentioned ARP earlier, and without broadcast, ARP would not work and switches just would not function. So let's talk specifically about Ethernet IP traffic. What is SIP? You may have seen this. CIP, SIP, however you want to say it. SIP is Common Industrial Protocol. It's an ODVA standard for communications. It covers I/O control, device configurations, data collection, and industrial automation and control systems. So as a former IT professional, when I first heard the term Ethernet IP, I was immediately dismissive, and that's not a thing. This is just because it was never explained what Ethernet IP was. Specifically, Ethernet IP with the big N/IP, it's the branded term for Common Industrial Protocol, or SIP, transmitted via the media of Ethernet. The IP actually stands, in this case, for Industrial Protocol, which is unfortunate because that also stands for Internet Protocol in IT-based computer science, hence the confusion.
So if anybody is working with their IT professional or is another IT professional on the phone trying to learn about the plant floor, this constantly gets attention and provides confusion. Just this double use of IP, if you will.
And the overlap with the name Ethernet in the first place causes a lot of confusion. You're going to get looks like you've got three heads, or the assumption that you don't know what you're talking about. But now you understand the difference and why you shouldn't just refer to Ethernet IP traffic as Ethernet. So Ethernet IP communications can be split into two types, explicit and implicit traffic. This is based on two types of communication protocols that Ethernet uses, TCP and UDP. SIP explicit traffic uses TCP, or Transmission Control Protocol, and it's considered a reliable transport mechanism. What that means is that it verifies the connection, understands what a recipient should expect to receive, and verifies that it's received all of it. If it expects to see data and does not, TCP knows to retransmit that data. Because of the nature of reliable communications, it can be unicast only, strictly one-to-one, right? So think of a TCP message as a phone call. I call you, you ask hello, I respond, identify myself, and confirm that the communication has been established before we continue the conversation. HMIs, message instructions, program uploads and downloads, all examples of SIP Class 3 messaging. This type of communication has a 30-second timeout. Given this context, let's take a look at the other types of traffic. The SIP implicit traffic uses UDP, or User Datagram Protocol, to send messages. This is extremely low overhead. The TCP three-way handshake and data verification steps are completely omitted in the interest of reducing the time it takes for a message to get out. Instead of a telephone conversation, this is more akin to a radio broadcast, or what I'm saying right now. I have no idea if you're actually listening to me, but I'm going to go right on speaking, assuming that you've heard me. Implicit messages are Class 1 SIP messages, which are common uses are I/O control, drive control, produce consume tags. The nature of implicit messaging also allows communications from one to many recipients, multicast traffic, as opposed to unicast. Pay particular attention to the timeout values here. The default is 4 times the RPI, or requested packet interval. Rockwell hardware defaults at 20 milliseconds, meaning a timeout, or communication loss, will occur at 100 milliseconds, or 4 times the RPI.
So Dave, why is that important? Can you just reiterate there?
So what we're talking about a timeout is if you have a requested packet interval, basically the PLC is expecting to see some sort of data come in that time interval. If it does not within 100 milliseconds, you essentially have a break in the program. That's what's going to cause a lot of equipment to just drop their connection. That's when you're going to see that yellow triangle or exclamation point in RS links, and you're going to wonder, why did that drive go out? Well, it's probably because it hit the timeout.
And does that mean you have too much traffic on the network?
It doesn't necessarily mean you have too much traffic on the network, but it is a huge indicator that that is the case. What it does mean is that the PLC just simply isn't seeing what it needs to see in the appropriate amount of time. Most of the time, it is a result of too much traffic on the network, but it can be other things as well.
And what about explicit traffic? The timeouts on that were significantly different?
30 seconds. So full 30 seconds versus 100 milliseconds. So it's quite a big difference. Very important to keep that in mind when you're dealing with communications. So let's take another look at multicast traffic. In this example, the PLC needs to send a message to 2 PowerFlex drives at once, and it's going to use multicast to do that. As I mentioned before, the original purpose of multicast was to reduce network overhead by sending the message to multiple recipients rather than opening more connection sessions. Like I said, why take 3 trips for 3 coffees when you can get them all together, right? This here is an example of a broadcast message. The PLC is sending messages to every device on the network. Upstream, there's another switch connected to a bunch of other devices, which also broadcasts out of all its ports to anything connected there as well. So keep that in mind as you think of explicit and implicit traffic. If you look again at those timeout values, implicit messages time out at 4 times RPI or 100 milliseconds. So what happens to multicast traffic on an unmanaged switch? If this looks familiar, that's because on an unmanaged switch network, multicast traffic becomes broadcast traffic. Unmanaged switches do not have a mechanism to control and identify multicast groups because it knows it needs to reach particular recipients but has no way of identifying who those recipients should be. The switch simply broadcasts or floods the network with the message because to the switch, it's fulfilled the promise of reaching all the intended recipients, as well as every single other device on the network.
And I think that is a critical animation right there, because how often do you see that is one of the key situations happening on the plant floor, is that there's a series of unmanaged switches all acting in this manner, broadcasting traffic everywhere. That's pretty common for detrimental situations, right?
Yeah, absolutely. We see it every day, all the time, and the just common thinking was, okay, the switch works fine on its own, but what happens when you start connecting devices? So the technology behind identifying multicast groups is called IGMP snooping. What this does is allow the switch to examine data passing through it, right? So IGMP snooping, it being on, is well and good, but it's also ineffective unless there's a designated IGMP snooping querier, which is actually responsible for identifying which multicast recipients should actually be receiving the message. The combination of these two features allow multicast traffic to be controlled and thereby reduce the total amount of traffic on the network. Here's an example of an I/O graph from a WIRESHARK capture. Here's a good example of what a managed switch can do. At the top, it's clear the network is seeing about 2,400 packets per second, or PPS, close to all of which is multicast traffic, as indicated by that red line. In a typical automation system, we deal with extremely small amounts of data at very high speeds, so really a normal amount is about 80 to 120 packets per second. When this same capture is graphed with multicast traffic management, the green line at the bottom indicates this, and it shows a dramatic reduction in the amount of traffic the network is seeing. So we're going from 2,400 plus packets per second down to about 100. Huge difference. Now, you might be thinking, a switch can easily handle 2,400 packets per second. What are you even talking about? That's correct, but the issue isn't exactly the switch's performance. The issue is the fact that the endpoints connected to the switch have limits on how much data they can process. Example is some specifications showing the packets per second values that various Ethernet interfaces can handle. For example, the very common EN2TR can handle a total of 5,000 packets per second. If you use IAB, Integrated Architecture Builder, to simulate your network, it will calculate what percentage of your network adapter is being used. And typically, it's not recommended to exceed 60% capacity. Also take into account the number of connections any particular interface can handle overall. If, for example, an Ethernet module can only have 128 TCP connections open, that would mean that any Ethernet IP communications are limited to that number. So any of the communications out there require an initial TCP connection to be established regardless of explicit or implicit messaging. So if, for example, a piece of Ethernet cable is receiving EMI, electromagnetic interference, and turning some zeros to ones or vice versa, the TCP error correction mechanism goes into play and retransmits. This occupies even more network bandwidth and can easily cause communication disruptions. All Ethernet cable is not created equal. The correct selection of Ethernet media is unimaginably important in an automation environment, but that's a whole other topic that I won't get into now.
I guess, Dave, to kind of summarize that section, that's a big area where you see a lot of challenges often, right? Just that.
I would say at the moment, this is the number one issue. There's simply, it's nobody's fault. It's not something that was, planned to happen, but that really underscores the importance of planning and building out a scalable system. Because the bottom line is that unmanaged switches do not scale to what we need these days to make those data collection and data-driven decisions.
Yeah, and I think you made a point about IGMP snooping and unmanaged switches, and I think one of the things we've also seen is if you use a traditional IT switch on the plant floor, it typically doesn't have features like IGMP snooping enabled, which then, as opposed to a switch designed for the plant floor, by default, they almost always have features like that enabled to manage plant traffic.
So some context behind that. In a typical IT system, multicast traffic is not really relevant. It's rare at most. At the best, I would say. We see way more multicast traffic in an industrial environment, just given the nature of the endpoints. Your typical PC isn't doing anywhere near as much multicast traffic as automation endpoints. So, and to your point, we have definitely run into a ton of situations where it's like, oh, well, we have IGMP snooping enabled, but there's no querier. So you don't really have any positive effect without both of those active.
Right. Okay, great. So it's really important that everybody kind of understands the difference in that traffic and what managed switches do in that regard. And then this section is additional areas that we should be looking as our networks grow, right?
Yeah.
Great.
Yes, absolutely. Okay, so what else can you do to limit the amount of traffic on the network? If you recall the broadcast domain, limiting that broadcast domain is a possible solution to reducing traffic overall. What do I mean by this? We could ensure, for example, that only devices connected to switch 1 can communicate with one another, and then switches 2 and 3 could also be segmented, or even all of them together. And how would you accomplish that? So this is done by implementing a technology called VLANs, or Virtual Local Area Networks. In this example, we've got 16 access switch ports that we want to create 4 independent networks on. So we simply take the individual switch port and make it a member of the selected VLAN. And then any communications that need to go from VLAN to VLAN can be accomplished via routing. This is what it would look like on a single switch, but what would it look like overall? Take this example. We have a process facility. This green area is a process area. Blue is a packaging area. Each area has 3 machines that are linked together. So recently, cameras, for example, have been placed on these automation control switches, but it's resulted in rampant problems because they consume so much bandwidth and disrupt the control network. These cameras are used in both the packaging and process areas, and they operate together. So the goal here is to create a separate VLAN for the cameras. They're designated VLAN 20 in green. A layer 3 switch or router is added to connect the control switches together. These red connections between the switches altogether indicate VLAN trunks. These can carry the traffic of all VLANs in between the switches. Essentially, the camera network on VLAN 20 can all be connected regardless of the physical location of where they are in the plant or facility, process, packaging area, same VLAN, they would perform as if they were all connected to the same switch. That data is being traversed from switch to switch over those VLAN trunks, and you can communicate regardless of physical location. So the layer 3 switch, if those cameras needed to communicate with anything on another VLAN, would be able to handle that by routing or doing inter VLAN routing. So what the ultimate effect of the VLAN is it is protecting the control traffic from what's going on the rest of the network. It's going to contain disruptions like a broadcast storm / layer 2 loop into just one VLAN and disallow it from propagating across the entire network. And it's going to allow the higher bandwidth applications, like in this example, the camera, to operate independently. This last section is improving visibility, or again, why your unmanaged switch isn't really helping you. WIRESHARK, I'm seeing a lot of use of WIRESHARK, but unfortunately a lot of folks aren't doing it properly, right? So it is an excellent and free tool available for public use, and it does packet capture. Well, that's great. I haven't seen it implemented properly in most cases. Usually what does get captured is irrelevant data, and most likely way too much of it, and the propensity for people is to just see things that aren't there. They're chasing after red herrings and wasting a lot of time. So the main problem with attempts to use WIRESHARK stem from not understanding what's seen and not understanding where to capture the data. So WIRESHARK requires a span, a switch packet analyzer, or port mirroring to be active. What this does is mirror a copy of the traffic from active switch ports to a single monitoring port. Without this, all that can possibly be seen is that multicast and broadcast traffic, because when you plug into that switch running WIRESHARK on your PC, you become a node on that network. You cannot observe what's going on the switch unless it is hitting your interface. Okay? So another large problem, apart from not understanding the multicast and broadcast aspect, is that the packet captures are occurring in the wrong place. So consider your typical office. You have computers which connect to a server sitting somewhere, and the communication is from the client, you, to the server. We'd refer to that as north-south traffic or upstream-downstream traffic. All the traffic passes through this switch to reach the server as an endpoint. Therefore, it makes sense to mirror the ports on this switch. Now, in a typical automation network, there might be an occasional need for a PLC or an HMI to communicate with an upstream server, but the vast majority of the control traffic on the network is from device to device. So you could describe this as east to west traffic, data moving laterally across a single switch. So the issue arises because 9 out of 10 times, the endpoints are all plugged into an unmanaged switch, which cannot be port mirrored. So that location is out for mirroring. So logic dictates the mirror on the ports. If you can't mirror those ports, you can mirror on the upstream switch, right? But remember, only a tiny fraction of that traffic passes through that managed switch. So the port mirror is simply never going to see data passing between the PLC, I/O drives, and the result is basically irrelevant data. So to make matters worse, it's probably a flat network on the automation side, which logically looks like a series of addresses. If there's a problem, it's virtually impossible to trace the source of the problem, even if you do have the IP address. What's the right way? The right way is to use a managed switch that's capable of port mirroring and have all your endpoints connected to it. These access switches are designed not only to optimize performance within a network, but more importantly, keep the other stuff out and protect the performance of your network. Then in the event something does happen on your network, you'll be easily able to identify the source of the problem and not waste hours on hours trying to track and trace it. So this is the fundamental means by which monitoring systems such as Clarity or any of your other cybersecurity solutions will work, using these correctly configured port mirroring sessions. So about 4 years ago, when I first started talking about these topics, pushback was persistent. it's cheaper, it works now, why should I change anything? My network's air-gapped, I only have islands of automation. All of these questions and answers came up. Nowadays, as the demand for data is accelerating and causing the pace of interconnected systems to accelerate as well, the line between IT and OT is as blurred as ever. So the fallout is really in the form of these enormous unmanaged networks that are unpredictable, uncontrollable, and in the event of problem conditions, completely undiagnosable. Just from lack of visibility, not understanding where anything is located because of that flat, unmanaged network. Hopefully this has given you all some insight into Ethernet and maybe even answered a few questions that you might have had out there. Thank you for tuning in today. If you have any questions on today's topic, please contact your Rumsey rep or any member of our ASG team. My contact information is right there on the screen. Don't forget that the specialist team will be hosting these tech talks every Tuesday and Thursday through the end of May. And there's a link there that will take you to the full schedule. So please join us again soon.